Hello class, welcome once again to our discussion today. We'll continue our topic on the review of our discussion on rectilinear motion. So this is our third example. Okay, so here's the problem. The spring-mounted slider moves in the horizontal guide with a negligible friction and has a velocity v sub 0 in the s direction. As it crosses the mid-section or mid-position, so here's the illustration class. This is the mid-position where s is equal to 0. So at this position, s equal to 0 and t is equal to 0. So the two springs together exert a retarding force to the motion of the slider, which gives it an acceleration proportional to the displacement. So take note of this: acceleration proportional to the displacement, but oppositely directed and equal to this a acceleration equal to negative k squared times s, where k is constant. So the constant is arbitrarily squared for letter convenience in the form of the expressions. Determine the expressions for the displacement s and the velocity v as a function of time t. Okay, so we will solve this problem, class, in two ways. So here's our first solution. Solution number one: since the acceleration is specified in terms of the displacement, so the differential relation v times dv equal to a ds may be integrated. So now the question is where this relationship is coming from. So again, so from the basic concept, so we have the velocity. Velocity is just derivative of the displacement, that is ds over dt, right? So, sorry, this is ds over dt. Okay, and we know that acceleration is just the derivative of this velocity. So we have acceleration is equal to dv, derivative of the velocity with respect to time. Okay, so now our goal here is to derive this. So you might ask where this relation is coming from. So it's just taken from these two basic relationship class between velocity and acceleration, of course, with respect to this displacement. So from here, if we solve for dt in terms of the other factors, so we have dt. So what you're going to do is cross multiply dt. You cross multiply dt, cross multiply v, or exchange position of dt and dv. Sorry, dt and v, and express dt in terms of the others. So we have ds, our dt is equal to ds over v. Okay. Now, if we let this equation as our equation 1, so let's call this as our equation 1, and let's call this equation here as our equation 2. Okay, now if you are going to substitute, so this is our equation 2. If you are going to substitute 1 in 2, so 1 in 2, so we will have a equal to dv dv over sorry, so this becomes dv over dt, where dt is equal to ds over v. So over ds over v, which when you simplify this one, so it will give us because okay, so this becomes division of fraction. So this becomes dv over 1. Okay, dv over 1, you invert the divisor. So this becomes dv times v over ds. Okay, all right. Or when you simplify this one, then cross multiply ds. So we have a times ds, a times ds equal to v. Just rearranging, no? You can write v first before dv. So v times dv. Okay, so this is it. Okay, we just interchange the position. Okay, so this is where this is taken from. But we are given a, given a equal to minus k squared s. So substituting. So instead of writing a is or let's just follow this expression class, interchange the position. So we have v dv. Okay, so v dv equal to a ds. Then substituting the value for a, where a is equal to minus, you have a equal to minus k squared. Okay, k squared times s. So that is for our a, but we have ds also. All right, so we have ds and we have v dv. Now when you integrate both sides, so what will happen is something like this. Okay, integrating both sides, so this will happen when you integrate without the limit. So we have the constant of integration, so we have to introduce the constant of integration here. Okay, so this is the one. Okay, or so from here, if you are going to simplify this one, we have when you integrate this, so applying the formula for the integration, so we have here the power. We have power here is 1, so 1 plus 1 2, that's why you have v squared, then divided by, because you have v to the n plus 1 over n plus 1, so we have 1 plus 1 2, so this is 1, this is the 1, then divided by 2. All right, equal to, so the integral of this with respect to s, so k is constant, so you just isolate this constant, then integrate s, so this become s squared over 2, right? Then plus c1, so that's why we have this. After integration, we got this result. Okay, okay, so I'll delete this part. So here from this result, when we let s be equal to 0, meaning initially, no, where s is equal to 0, meaning at this mid position. So at this mid position is equal to 0, v is equal to the initial velocity, meaning the velocity here is initial at this position. So that when you substitute these values here, so we'll be able to solve for c1. Because when s equal to 0, so what will happen when this equal to 0, So the whole thing here becomes 0. 0 divided by 2, that is still 0. So therefore, we solve for C1. C1 is equal to, we have V over 2. But our V is equal to V 0. Our V here is equal to V sub 0. So therefore, this becomes, our C becomes V squared over 2. So with this condition, class, okay, we change V to V sub 0. And the velocity becomes something like this, because from here, okay, so this is our relationship here. We substitute the values for C1 and then simplify. So cross multiply, then combine them, then take the square root on both sides. So we got V equal to plus square root of V initial velocity minus k squared s. Okay, so this is just algebra, class. So after substituting this one, then combine it here, then cross multiply or multiply both sides by 2 just to eliminate the fraction here, so that you will deal only with this one. So of course you have the C1 here. This is our C1. Okay, then after simplification, so we get this V, so we take the positive value of the velocity. Now the plus sign of the radical is taken when V is positive in the plus S direction. So that's why we take the positive here. So this last expression may be integrated by substituting V equal to ds over dt. So when you do that, so we'll get this one. Okay, so we have the integral of ds divided by the square root of V squared minus k squared uh, times e squared, and that is equal to the integral of dt plus c2. So c2, that is a constant, or 1 over k, from the formula, no, this is the d over u. Sorry, yeah, d over u, but in this form we have this is the inverse trigonometric function. So we have the form of du over the square root of u squared minus a squared minus something here. It follows that form of the formula. So when you integrate that, when you have the complete du, then you integrate it. So we'll get this dt plus. So this one is just equal to this, or using the formula of the differential calculus and also the integral calculus. So we get 1 over k, inverse sine of ks divided by v sub 0 plus t plus c2. So with the requirement of t equal to 0 when s equal to 0, so the constant of integration becomes c2 is equal to 0. Okay, because with this a condition t equal to 0, so when you substitute it here, so we will be able to solve c here, c2, second constant. After substitution, we get this c sub 2 equal to 0. And we may solve the equation for s, so that s is equal to v sub 0, or the initial velocity divided by the constant times the sine of kt. Okay, so the velocity is v, which is equal to the s dot, meaning derivative the displacement, which gives us this v is equal to v sub 0 cosine kt. So meaning from here, when you take the derivative of s here, so this is our displacement. So when you take the derivative displacement, so this become s dot. So s dot or s prime in our differential calculus. So we have the derivative of s is equal to v. Okay, so this is a constant. Okay, we have since this is constant, you can remove this one, because when you find what is the derivative of sine, derivative of sine is cosine, right? So we have derivative of sine u, derivative of sine u with respect to t. is equal to, this is cosine u times the derivative of u with respect to t. Okay, so what is our u? Our u in this case is equal to this one, so kt. So derivative of u, derivative of kt is simply k. So you have k divided by k. So that's why the k here is gone. All right. So therefore, our expression for the velocity is equal to final velocity is equal to the initial velocity times cosine of k times t. Okay. So this is the first solution, or solution number one. Now let's go directly to the second solution, or the other way of doing this. So second solution, or solution number two, since A is the second derivative of the displacement, so the given relation may be written at once as something like this. So S double prime or S double dot plus K squared S. So the double dot here indicates second derivative, first derivative, and then take another derivative. So you have double dot here. So it means that you take the derivative of the displacement twice. So equal to 0. Okay, so from this solution, and this is an ordinary linear differential equation of the second order for which the solution is well known. Now, remember from our differential equation, if you're done, if you have passed the course in differential equation, so you're expected to know the how to solve this kind of equation. So this is an ordinary linear differential equation of second order for which the solution is well known and is written as S equal to A sine kt plus B cosine kt. All right, and A, where A, B, and K are constants. Now, substitution of this expression into the differential equation shows that it satisfies the equation, provided that K is constant. This K here are constants. The velocity is, as we know, this is the derivative of the displacement, which becomes something like this. Okay, so when you take the derivative of this one, so the result, no, this equation here, when you take the derivative, this is now the result. So derivative is, which is the velocity, and the initial condition v equal to v sub 0 when t is equal to 0 requires that a is equal to v sub 0 divided by k. And the condition s is equal to 0 when t is equal to 0 will give us b is equal to 0 also. So therefore, so the solution is, from our differential equation, we have s equal to v sub 0 divided by k sine kt, and v sub 0 after differentiating this one. Okay, when you differentiate this with respect to t, we got this v equal to v sub 0 cosine kt, similar to the first solution. Alright, so that's all for this problem. Thank you very much, and I again hope to see you in our last example for this topic. Bye.